Should I share my screen to start? Yeah, okay.
Yeah.
Okay. How's that?
Yep.
I think it's coming.
Okay, so should we just admit everybody now?
Yeah.
That sound good,
Sounds good. Yeah.
Nadia? All right.
Yes. Hello, everyone. Good morning. So can everybody hear us? Can everybody see the screen?
Yeah, all good.
All good. Okay, so in this case, I guess we can start. So we already have the audience coming. So Ricardo, so I'll let you introduce the speaker for today.
Yes, no problem. I can do that. So we have Professor Tim Moroney from Queensland University of Technology. Tim is an expert in scientific computing, in numerical analysis, and computational mathematics in general. And it's a great pleasure for us to have him giving this series of lectures. So we have two speakers, and we'll do the introduction of the second speaker later on. But so just thrilled to have Tim with us, and we will not take much more of his time.
Brilliant. Thanks, Ricardo. Thanks very much for the invitation as well. See some familiar names in the participants list, so welcome to all. Yeah, so in the interest of getting on, thanks for coming. Here's the outline for what the plan will be. So we've got 5 lectures, and today we're going to do an hour on Arnoldi methods for eigenvalues. And then whatever we don't get finished today, we'll finish in the next hour tomorrow. And then Chen will talk to you for 2 lectures on GMRes for linear systems. So both of these are methods for solving important problems with sparse matrices. So that's the unifying theme. Today is eigenvalues and GMRes is linear systems. And then in the final lecture, I'll be back for an hour to talk about extensions, stuff that we may not have covered off during the first 4 lectures, but which might be interesting to talk about. Okay, so if you're here, you probably know something about sparse matrices or would like to, in which case, great. They turn up a lot. Okay, there are heaps of applications that deal with sparse matrices. And when we say sparse matrices, we mean matrices with usually many entries, but most of which are 0. Okay, so they're usually large in terms of the number of rows and columns, but the number of actual numbers that are not 0 might not be so many. All right, so a good working definition of a sparse matrix is any matrix for which it's advantageous to take advantage of this fact. Okay, typically by storing and operating only on the non-zero values in the matrix. Classic case where this will come up is when you're discretizing a PDE. Okay, so let's go back to here. Each little row in this matrix could be an equation for a particular node in your mesh. And because you're dealing with differential operators, you need some knowledge of what's going on in your neighborhood, but you don't need to know about the entire mesh. All right, so every node's equation involves the derivatives involving nearby nodes. All right, so the way that they're connected up in your mesh gives you different patterns in your sparse matrix. So it's really essential that we take advantage of this when we're dealing with very large systems of equations. Otherwise, you just don't have the memory and the time in your life to solve the problem using traditional dense algorithms. So there are different storage formats you can have, coordinate format and CSR and CSC and so on. Mostly we won't go into those sort of details here. We're going to rely on the fact that whatever storage system you've come up with, it's able to multiply you a matrix by a vector, which is like the minimal possible requirement you could ever hope. It's going to turn out that's basically all you need, right, for the algorithms here is be able to multiply a matrix by a vector. Okay, and because it's sparse, the algorithms to do that will typically be quite efficient. They'll just touch the non-zero entries only. So that the cost of a matrix vector product can be quite cheap, relatively speaking. Okay, so our iterative methods are only going to build upon that, right? So we have Arnoldi for today and GMRes coming up. And look, wherever you solve interesting problems, if they involve PDEs and other things as well, you'll have sparse matrices. So there's heaps of applications for this sort of thing. Okay, so the eigenvalue problem is, one of the two big problems in linear algebra, the other being linear systems, of course. For today, A will be large, sparse, well, actually the examples won't be so large. Sparse, non-symmetric. Let's take the non-symmetric case for today, but we will assume diagonalizable. Okay, that's useful for developing the theory. And you can get into deep conversations around what it really means when you have very bad conditioning of your eigenvectors to think too much about spectrums of matrices and those conditions and so on. So we'll take that everything is nice for us in our matrix. It can be complex, right? Everything works fine in the theory, but we just present real examples. In fact, I've just got one example. Now, because this is a very large matrix, our goal is not to compute all of the eigenvalues of A, but only some. And for two good reasons. The eigenvalues that we'll be aiming to get are the extreme eigenvalues of A, so those that are near the edge of the spectrum. Now, it's going to turn out that those are the ones that the method naturally wants to pick out for us anyway. But they're also often the most relevant in applications. Okay, so the ones at the extreme edge can tell you things about stability and so on of a system, for example. Oopsie, hang on, come back. But we're going to start with the simplest idea, which you may have come across before, which is called the power method. And we're going to use that as a stepping stone to the main focus, which is going to be the Arnoldi method. Okay, so if your matrix has a dominant eigenvalue, that is to say it's got one that's bigger in magnitude than all the others, then the power method could be for you. Okay, so this is a method that will work for a situation like this. We're assuming the matrix has a complete eigenbasis. Okay, so it is diagonalizable. And we're going to choose a starting vector B at random. Okay, so later on in the lectures, B will be a right-hand side for a linear system, in which case you don't get to choose it. But for the eigenvalue problem, you may as well just pick a random one to start with. Okay, and we're going to see that really it doesn't matter as long as it's got some component in the direction of the dominant eigenvector, then the method's going to work. Okay, so we're going to write this starting vector as a linear combination of our eigenbasis. We don't know what this basis is, of course, but the theory doesn't care. You write down the sum involving these unknown coefficients, and let's split out the sum involving the first term separately. All right, so this is the term that involves the dominant eigenvector, all right, the one that goes with the eigenvalue of largest magnitude. Okay, and these are all the rest of the terms. Okay, well, if you multiply that matrix by A, then, well, you just multiply each term by A, of course. But these are eigenvectors. Okay, so A times x1 is lambda 1 times x1, and so on. A times xi is lambda I times xi. And you could do that again, right? If this works once, you multiply again through by A, and you'll get lambda squareds, and you multiply again, you get lambda cubes. So in general, if you multiply through k times, you get a to the k times b, and you get this lambda 1 to the k, and then all these other lambda i's to the k. Okay, so you can start to see what's going on here. Lambda 1 is the biggest, right? The biggest in magnitude. So when you pull it out the front, and you've got lambda 1 to the k sitting out here, distributing over the rest, in here, each of these factors is now less than 1. Okay, because lambda 1 is the biggest. Okay, so that's all of that is going to go to 0 as you take k to infinity. Okay, so the bracketed factor here, this expression involving at first all of the eigenvectors, the components in all of the other directions decay off, okay, at this particular rate. And so the conclusion is the direction of a to the k times b tends to the dominant eigenvector. Okay. So I'm going to give you a little demonstration of that. Okay, so this is a not especially large 20 by 20 matrix, but it is sparse. And we're going to apply the power method to this matrix. Okay. So of course, this is MATLAB. It's got built-in algorithms for calculating eigenvalues. So we're going to benchmark against this one here. I set the random number seed to the defaults. I already know what to expect. There is a dominant eigenvalue for this matrix. It's 2.4 roughly. So let's see how the power method goes. Okay, we really do just pick a random vector to start with. Okay, as long as it's got some component in the direction of the dominant eigenvector, which it will, then we're going to be okay. Now, the way that we presented this on the slides is just to multiply by A again and again. In practice, that's going to blow up the magnitude of the entries in that vector because this largest eigenvalue is bigger than 1. So we don't overflow or get into any trouble. We're actually going to normalize the vectors as we go. Okay, so we'll normalize the initial vector, V1, we're going to call it, which is B divided by its length. Okay, the norm of B is this number here. It was just from the random vector, and we normalize it. Okay, so now we iterate. So we're just going to take 8 iterations. Here's my loop. And each step through the loop is just multiplying A by the previous vector, and we're going to store each new vector as a column in this matrix, capital V. Okay, so the first column is this first normalized vector. And as we run more and more iterations, you do see that the columns of this matrix start to approach a particular vector, right? We've got a couple of digits more or less unchanged, okay, for this, this 8 columns in this matrix. Okay, now that's a good estimate, potentially, of the dominant eigenvector. And so the question is, how do you estimate the eigenvalue? Well, a good idea is to use a thing called a Rayleigh quotient. Okay, so if you think about this, if this vector, this last one here, is approximately an eigenvector, then A times that vector is approximately lambda times that vector. Okay, so if you hit it with a V transpose, or a conjugate transpose at the beginning, then you're just going to pick out the eigenvalue times the norm. And since the norm is 1, you're going to get this estimate for the eigenvalue. Okay, so it's called a Rayleigh quotient. We don't have a quotient here because we've already normalized. If we hadn't normalized, the quotient would be, we divide by the length squared. Okay, so how does that compare? Well, actually, it's not too bad. Okay, we saw before it was 2.4 something, and this is 2.4 something, so great. As for the eigenvector, well, we can compute the residual. Okay, so A times V is supposed to be mu times V. After all, that's what it is to be an eigenvalue eigenvector pair. So this residual is a measure for whether this is a reasonable match. Okay, so we'll keep this in mind. This number here will be our benchmark, if you like. Okay, and so further iterations of this power method would just improve these refinements at this particular ratio. All right. Okay, so this is the power method algorithm as we've implemented it. So we choose this random b to start, and then we iterate. And at each step, if you want, you can calculate what the eigenvalue would be. In our case, we just waited till the end to calculate this estimate mu using the Rayleigh quotient. And as we said, this is the idea, right? To calculate, there's different ways you can imagine to pull an eigenvalue out of the eigenvector. You've got plenty of information, right? A times V is lambda times V. This is a good way to do it numerically. Okay, now let's just reflect on what we've done there. We started with B and we progressively calculated these products, AB, A squared B, A cubed B, etc. We'll ignore the scaling. Okay, we did normalize, but we'll ignore that for now. But then we just used the final vector in the sequence. Okay, so our estimate came from just here, right? This last vector. What about all this stuff? Okay, is this not useful information? Maybe we should be thinking of a way to incorporate all of this information in our numerical method. Okay, so that's the observation here. What we've actually built with this power method is a basis for this very special subspace that we're going to be hearing a lot about during these lectures. It's the star of the show. It's the Krylov subspace. Okay, so it gets a script K, a subscript M for the dimension. Okay, so it's got M vectors starting with B and going up to A to the M minus 1B. And in a sense, it's the most natural subspace you could ever build, given a matrix and a vector. Remember, we said that all we really assume that we can do with our matrix is multiply by a vector. So what could be more natural than multiplying by a vector again and again? And in fact, we did it naturally as part of the power method. All we want to say now is to take this idea more seriously and ask, well, what can we do with the subspace that we generated? Okay, so clearly this subspace captures something about how A acts on vectors. Okay, so there ought to be some information about the eigenvalues lurking in there. And yet in the power method, we throw nearly all of it away. Okay, and just use the final vector. So our question here is, how can we make better use of this full subspace of information? Okay, so this is leading us to the idea of projection methods. Okay, so you start with a large dimensional problem. Okay, so our large sparse eigenvalue problem. Not so large in the example, but you can imagine it's large. And we're going to project this problem down onto a small dimensional space. Hey, what about the Krylov subspace? That sounds like an idea. Because in the Krylov subspace, we can solve it exactly, okay, and cheaply because it's small dimensional. And then we're going to lift the solution back up to the full scale to obtain an approximate solution to the large dimensional problem. Okay, now this is an idea that sees applications in all sorts of different areas. It's certainly not unique to Krylov subspace methods, this idea of projecting down onto a smaller dimensional space. But, you know, we'd better ask ourselves, what does it mean here? Right, what do we mean to project the eigenvalue problem onto a Krylov subspace? Okay, sounds good in principle. What do we actually mean by that? But hang on a sec, maybe we're getting ahead of ourselves here. Here's the Krylov subspace. As we've written it down, the span of all these vectors, we're keen on the idea that there's useful information in here. But actually look at the vectors involved here, all right? If you thought that the literal vectors b, a squared b, and so on would be a good choice of basis for this space, then you're going to be in for a bad time, all right? Because the whole point of the power method is that each of these vectors gets more and more parallel, okay, as you iterate. Look, this almost looks like the same vector from one column to the next. That's the worst possible choice of basis you can imagine numerically. You almost have linear dependence. So we certainly don't want that. So the second question, which we're going to have to answer first, if we're going to make any progress here, is how could we build a well-conditioned basis for this Krylov subspace? Okay, the actual vectors on the page here would never do numerically, right? You'd get nowhere if you tried to use that as your basis. Okay, so we're going to have to solve that one first. Now, you may have heard of the Gram-Schmidt process. If you have, great, this will look familiar. If you haven't, you're going to see a variation of the idea in this Arnoldi process, as it's called, which is, you know, reasonably described as being Gram-Schmidt on the fly. Okay, so what we're going to do, we're going to start again with the same initial vector as before, and we are going to multiply that by a, just like we did before. But before we go including this in our matrix, we orthonormalize this new vector against the first. Okay, so what do we mean by that? We mean we want the new vector to be orthogonal to the original vector. So we started with b, which we normalized, and that's v1. This vector here is a times v1, and it points in some different direction. And we know if we just keep on multiplying, it's going to end up pointing in the same direction more or less as the one previous. So we're going to avoid this problem by subtracting away its projection onto the vector that came before. Okay, that's the key idea. And we're going to carry on scaling the results by its length so that it's normalized. Okay, so this vector w becomes w minus its projection onto v1. And v2, the second vector in our basis, will be the normalized version of that. Okay. Now you notice to do this calculation, we need two scalar quantities. We need this dot product, w dot v1, and we need this norm, right? After we've done the subtraction, we take the norm. So we're also going to record those two numbers as we go. And for good reasons, as you'll see, we like to record those numbers in a separate matrix that we're going to call H. Okay, so here's the first dot product in H11, and here is this W vector after you've subtracted off the projection. Okay, so that's now orthogonal to V1, but it doesn't have unit length just yet. So here we normalize. Okay, that gives us a second number to record, this norm of W. We'll stick it in the second entry of H. It's only got two entries at the moment. And then we normalize, and that becomes our second column of V. Okay, so by doing this, we're still capturing the same space, right? This basis will span the same space. It's just linear combinations of the B, the AB, the A squared B, but it has perfect numerical conditioning, right? Couldn't ask for anything better than an orthonormal basis, okay? So we're going to repeat this process m times, and this is called the Arnoldi algorithm. Okay, so m is 8 here, j goes from 1 up to m. This is us computing the next vector. So this is the classic building up the basis for Krylov subspace. You take the vector that you had before and you multiply it by a. And then here, we're orthogonalizing against the previous columns. Okay, so there's all these dot products to calculate against all the previous vectors, and there's j of them, right? Because we multiplied vj to get the next. So there's j previous ones, so there's j dot products. There's j subtractions to perform. And then finally, there's the norm at the end of doing all that. So after this step, here, the vector is orthogonal to everything that came before. And then after this step, it's normalized. Okay, and we've kept track of all of the intermediate calculations, these h's, record all of those dot products and the norms. Okay. Okay, so the columns of V now will form an orthonormal basis for the Krylov subspace. So there's none of this, vectors looking like the columns before. Okay, we've got a very well-conditioned basis. Couldn't be better. Spans the same space, right? But well-conditioned. And we've also kept a record of all of these dot products and norms that we've stored in this matrix H. Now, just by looking, you can see here that H is rectangular. Okay, think about the first column. We had a dot product and then a norm. Okay, and then the second time through, we had two dot products and then a norm. All right, so it's got one more row, then it has columns, that's fine. And, the structure of it is what we say is upper Hessenberg. Okay, so it's not quite diagonal. It's got one entry below. Right, it's got one subdiagonal. Okay, so in the theory, we're going to call this HM bar to emphasize that it's rectangular. Okay, we'll have a square version to deal with shortly. Okay, so this is the Arnoldi process that we just went through. Start with a vector that we're picking at random, normalize it, and then run through this process. You might have wondered what happens if you get a 0 for this hj plus 1j. After all, you're about to divide by it. Okay, so that would be if the vector w was the 0 vector after all of this work. You should stop if that happens, okay? We will see a bit later on what the implications of that are, but it's actually good. If this happens, we call this a lucky breakdown, and you're good to stop at this point. Okay, so at any step, the columns of V will form an orthonormal basis for the Krylov subspace of that particular dimension. Okay, so we're building it up on the fly. We have also, as we go, generated this rectangular matrix HM bar, whose ijth entry is simply this hij. Okay, so this is the algorithm again. Let's see if we can derive a relationship now between the three matrices, right? We have A that we started with, we have V, which is the matrix with all of our vectors, and we have H, or HM bar. So from this line, we can rearrange to get Wj easily enough, and then we can put it back up here, right? This is just a statement of where all these vectors came from. We're working backwards. To get V, we divided W by its length, so W is the V times the length. But this W was the A times the V minus this, projection onto all the previous V's. So plonk that up here. And already we've got rid of the intermediate W. Okay, so you can think W was sort of a variable we used in our formulation, but it's not something we care about outside the algorithm. What we care about is A's, V's, and H's, and this is a relationship that just involves those. Okay, well, it just seems so natural to want to put A times Vj on the left here, and this term looks just like this term, but this is the next term along. Okay, so this is the sum of all these Hij's times the V's, and this is the final sum, the final term, I should say, in the sum. So the overall result is that we have this. A times Vj is just this sum from i's 1 to j plus 1 of Hij Vi. Okay. Now we can't leave it at that. We must surely want to write this in terms of some sort of matrix expression. Okay, well, let's do that. We've already got the V's as columns of a matrix. Here they all are. right? All m plus one of them, right? You actually will have noticed that the algorithm does generate you an m plus one vector at the end of it, okay? Back here, m was 8, of course, but we did get the 9th column, okay? So keep that in mind. So A times Vj is, well, it's V1 times H1j plus V2 times H2j, and so on, all the way down to Vj plus 1 times Hj plus 1j, plus nothing after that. Okay, but we've got all these vectors, so we'll just make sure we hit them with a 0 in this expression, and so this is correct. A times Vj is this whole operation on the matrix Vm plus 1 with this column of numbers. It's got the zeros in the appropriate places. And so in matrix form, this just looks like A times the jth column of Vm is Vm plus 1 times the jth column of Hm bar. Remember, Hm bar does have this upper Hessenberg structure. Okay, so altogether, this is our first Arnoldi relation, which is A times Vm equals Vm plus 1 times Hm bar. Okay, so let's confirm that this is holding for us. Left-hand side is A times Vm, so the columns 1 up to m. The right-hand side uses all of the columns, which is just all of V, but we'll emphasize it by putting the m plus 1 in there. Okay, these two matrices, they look good, in as much as they look the same as each other. And yes, okay, so to round off error, machine precision, these are the same thing. So that's confirmation that this first Arnoldi relation holds. Okay, now, what about this m plus 1 column? Well, we can always split it off. Okay, we can always keep the Vm part, which is also already sitting on the left, and split off this extra column and split off the corresponding final row of the Hm bar. So that leaves us with the square bit, Hm, still upper Hessenberg, but square, and this row which comprises only one non-zero value, right? This last row is zeros all the way through to this final norm. So you might as well write that as Hm plus 1m times Em transpose. Okay, Em just being the unit vector with the 1 in the mth position. Right, and now block multiply this out, and so we get our second Arnoldi relation. AVM is VMHM plus this single term, Hm plus 1m, Vm plus 1, Em transpose. Okay, so we'll confirm this one works. Is Em, well, I guess I can print it out so you see what I mean. That's Em, 1 in the mth position. Left-hand side is AVM as before. The right-hand side now has the two terms, VMHM plus the extra term. And yes, once again, those completely agree. Okay, and now the third and final Arnoldi relation that we're going to want is to take this starting point, but now hit it with a Vm star, conjugate transpose on both sides. Okay, so remember that the columns of V are orthonormal. Okay, so if I do this, I hadn't thought to demonstrate this, but I'll put it in on the fly here. Always risky doing things in real time with code, but there we go. Okay, so we've got dot products of every pair of vectors in V being either 0 or 1. Okay, dot product of a vector with itself is 1, and with any of the others you get 0. Okay, that's what it means to be an orthonormal basis. So we've got that when you hit a Vm star with a Vm, you get an I. Okay, at the same time, the m plus 1 column is orthogonal to the whole of Vm. Okay, it's been orthonormalized against the rest of the columns. That's what we do in our Arnoldi process. So if I take that product, well, of course, it's 0. Okay, 10 to the minus 15, okay? So that kills off this term, and we just get Vm star AVM is HM. Okay, now this one is great for us today because square matrices, right? Eigenvalue problems. So we're going to lean on this one a lot today. When Chen talks to you about GMRes, it's the rectangular version with the HM bar that plays more of a role. Okay, so here we go. 3 Arnoldi relations. A is our n by n matrix, n is typically large. V carries m n-dimensional vectors. Vm plus 1 just carries one more, just along for the ride. And HM bar is rectangular upper Hessenberg. HM is square upper Hessenberg. Right? You just remove the final row. And we're going to be caring a lot about HM. Okay. So we have answered our second question from earlier, okay, which is how do we build a well-conditioned basis for the Krylov subspace? Okay, the answer is that the Arnoldi process generates an orthonormal basis for Km in the form of the columns of Vm. Okay. Furthermore, we have this Arnoldi relation that tells us that Vm star AVM equals HM, okay, where HM is upper Hessenberg, okay, square. So now we can return to the first question. What does it actually even mean to project the eigenvalue problem onto a Krylov subspace? Okay, what do we mean by that? Okay, well now, we're going to consider what it means to take an arbitrary vector in this Krylov subspace, and if it belongs to the Krylov subspace, that means, by definition, it can be represented as a linear combination of the columns of V. Okay, so this vector is Vm times y for some coordinate vector y. All right. Now let's consider what happens if you multiply this by a. Okay, so you form a times u, and most likely this new vector does not belong to the Krylov subspace. Okay, u does, but u could just be, just any vector at all, and it's not like we run the Krylov subspace on and on forever, capturing every possible a times v. Right, we stopped at this dimension m, and we picked a vector here, we multiply by a. It probably doesn't belong to the Krylov subspace. But whatever it is, it's a times vmy, that's for sure. And now we're going to orthogonally project this vector. This is more of a thought experiment. I'm not going to actually do any of this, but to understand what the problem looks like in the Krylov subspace, the projected version, we imagine orthogonally projecting this vector that we got, a times u, back onto k. Okay? So Vm is an orthonormal basis. So Vm star is an orthogonal projector. Okay, so Vm star times AU orthogonally projects AU, whatever it is, back onto K. Okay, AU is Vmy, so this is Vm star A, Vmy. So now it's just pattern matching. Okay, so this does take the form of Vm times some matrix times y. Okay, so now we can identify the projected matrix, the thing that corresponds to A, but in this m-dimensional space, is this matrix Vm star AVM. Hey, we saw that just a moment ago. Okay, Vm star AVM is HM. Okay, so the Arnoldi relationship tells us that the matrix version of A in the Krylov subspace is nothing but HM. Okay, so that's already an interesting result. A matrix projected onto its own Krylov subspace is upper Hessenberg. Okay, and it's in particular given by HM. So this is the problem that we should now find eigenvalues of, right? The equivalent problem in the m-dimensional Krylov subspace is to solve the eigenvalue problem for HM. Okay, so that's exactly what we're going to do. Okay, so we can find the eigenvalues of HM and see how they compare to the true eigenvalues of A that we found earlier. Okay, so this is a very easy problem to solve. It's just a small square matrix. MATLAB will happily do that for us. We can sort these in descending order, just like we had done with lambda. And now what do we have? Well, we've got the dominant eigenvalue, quite well represented, but a few others. Okay, notice this second eigenvalue looks quite decent, and maybe even this conjugate pair is coming out okay. All right, so we're picking out more information than just the dominant eigenvalue and the dominant eigenvector through this process of the Arnoldi method projecting onto this Krylov subspace. Okay. So we've got eigenvalues, let's call them theta I, and eigenvectors yi of hm. And this is the small scale eigenproblem that we've just solved, which is easy, right? M is, some small dimensionality. And then we're going to map it back to n dimensions. Now, how do you map back? Well, this is an eigenvector, all right, that corresponds to this square matrix HM. So it maps back using VM, right? This corresponds to the coordinate vector of the eigenvector approximation, UIM, that we're seeking. Okay, so these are called Ritz values and Ritz vectors. Okay, so the eigenvalue we get here, these are, you can call them in the MATLAB file Ritz values, but we don't have Ritz vectors yet. Let's get the first of them, shall we? Okay, so I'll just use eigs here to get the eigenvector that corresponds to the eigenvalue of largest absolute. This is of H, of HM. Okay, so this is a small scale 8x1 vector, but what we do, that corresponds at the large scale in dimension n of Vm times y. Okay, so this is just the coordinate vector of the thing we're going to call the Ritz vector. Okay, so this is the estimate of the eigenvector that the Arnoldi method is giving us. Okay. So once again, we can calculate the power method residual and compare against the Arnoldi method residual. And yeah, this is a little bit better. Okay, so we've got the A times U is roughly, this theta 1 times U, and it's more accurate than the power method was. But the power method didn't give you any of these. Okay, so we're also getting, for our money, some estimates for these additional eigenvalues of A. Okay. So there's some promise here. Ideally, these would be good approximations of the true eigenvalue-eigenvector pairs of A, and at least our first inspection of this seems to confirm that we're making some progress. But you're always going to want to know how good you're doing. Okay, so a numerical estimate is one thing, but a sense for how accurate it is another. Now, what we can do is what we did here and calculate the eigenvector residual, because you can compare A times U with theta times U. But notice to do that, we scaled the problem back up here. Okay, so we had a lovely small scale result, cheap to calculate, cheap to work with. And then we scaled it up to the big n-dimensional vector, and then we found the eigenvalue residual, the eigenvector residual. It would be nicer if this residual was something we could monitor at the small scale, okay, and only map up to the n-dimensional scale when we were satisfied that this was going to be sufficiently accurate. Okay, so let's see what we can do with our Arnoldi relations then. So A times UM is Vm times Ym. Ym is the eigenvector you get from your small scale HM eigenvalue problem. Okay, well, AVM, we've got a result for that. The second Arnoldi relation that we had is the one that splits it out into Vm HM plus the extra term, HM plus 1m, Vm plus 1 EM transpose, and that's all multiplying Ym. Okay, so let's just distribute the ym across both terms. And notice that we've got an HM-ym. Okay, well, ym is an eigenvector of hm, so HM-ym is theta m ym. That's what ym is. It's an eigenvector of h. Okay, so theta, we'll just shuffle out to the front. And we've got the second term we haven't done anything with. Okay, but here's vm-ym again. Okay, vm-ym is Okay, so this is the vector at the n dimension scale. Well, look at this, aum, theta m, Okay, so the eigenvalue residual, taking the difference between these two, is in fact given by information that you can calculate entirely at the scale of m, okay, the small dimensional problem. Okay, so it's given by hm plus 1m times vm plus 1 em transpose ym. And you'd probably like to know the norm of that result, okay, to know if that's big or small or if it's satisfactory or not. So take norms. hm plus 1m is just a number. Vm plus 1 is normalized, so its norm goes away to just 1. And what is em transpose ym? That's just a slightly odd way to write the mth component of ym. Okay, so the calculation that you can do to determine your eigenvalue residual at any step is just to look at the m plus 1 mth entry of h and the mth component of your small scale eigenvector, and that should be your residual. Okay, so we can verify that this is true. Okay, so hm plus 1m times ym in absolute value is exactly this Arnoldi residual. Okay, well, just to finish with then, before I open the chat for questions, there is this lingering question about what happens with the lucky breakdown. Okay, so let's go way back to the algorithm. Keep going. Oh, power method, too far. The algorithm wanted us to divide by hj plus 1j, but if hj plus 1j is 0, then we probably shouldn't do that. But at the time I said, well, this actually is good news for you. This is called lucky breakdown. And now we see why. Okay, because by the time we've got our eigenvalue residual, that is exactly the quantity that sits in this position, right? hm plus 1m. If this is 0, then you have no error. Okay, you have a true eigenvalue eigenvector pair of A. And you say, well, surely is too lucky to hope for, but not so much. Now, in this example here, it's only going to be reached in the case where we crank this all the way out to the size of the problem. So I'll do that for you now. Let's go back to this Arnoldi process and calculate the full Arnoldi decomposition. So this H now has 21 by 20 rows because we cranked it all the way out to m equals to n. And if we have a look, this number is 0. Okay, it is essentially the number 0. Okay, so at this point, this is not behaving like an iterative method so much anymore. We've just computed a full Hessenberg decomposition of our matrix. So it shouldn't be surprising that we're able to get the full and correct set of eigenvalues and eigenvectors out in that case. Okay, so all the Arnoldi relations, I guess I can just rerun all of these. And we'll jump down to the ends. And sure enough, okay, this A times U times RITS 1 times U is 0. The difference is 0. Okay, and the shouldn't expect an exact match in this number, which is essentially the number 0, but our small scale calculation confirms that this is now correct. Okay, so, okay, no big surprise. We cranked it all the way out. We computed the full Hessenberg decomposition. So at least this is a validation that if you really do all of that work, you've basically recovered some sort of direct method for finding the full set of eigenvalues and eigenvectors. Now, in case you're wondering, there could be some, this might be anticipating a question. We didn't actually break the loop, all right? We just carried on all the way to the end. So what's going on here? Okay, so we've got apparently a V, which is 20 by 21. What? No, that can't be right? You can't have 21 orthonormal vectors in your 20-dimensional space. Okay, so it must be, this all looks good, this all looks good, but no. Okay, it must be that the final column in V is not at all orthogonal to all of the others. And if you look at the algorithm, that shouldn't be a surprise because we really did the division by zero at this step. Okay, we did actually calculate the norm of this thing, which on paper should have been zero at this point, but because of round-off error, it's never exactly zero. So we essentially just have a random normalized vector sitting in the final column of V right now. But it doesn't do any harm. You know, we don't use it. So in this case, we got away with it. Okay, so that is pretty much on time to finish for the first lecture on unholy. That does give us almost 10 minutes for questions. So I'm very happy to take questions either by the chat or if you want to ask a question in person. Just to flag where we're going with this, we're going to analyze the theory of this in the next lecture to understand what we should get for our money and why we think that it will converge to extreme eigenvalues and so on. So if you're wondering about all that stuff, that is coming in the next lecture.
Okay, thank you very much, Tim. So now questions. So I think at the moment our chat is empty. So if someone wants to ask a question, then in this case, just unmute yourself and ask. So I cannot see any hands neither. So maybe I should start just to warm up the audience. So Tim, so in your examples, so
Yep.
I mean, you said that they are not very huge anyway, but how far would you go with the dimension in real problems that you have been solving?
Yeah, I mean, this is a very good question. You know, practically you can run into trouble if you take your dimension too big because you can run out of memory. Okay, so think about that V. You're storing full dense columns, which are of the n dimensional scale. So one answer to that question is you can run until you can't run anymore. Okay, and you've filled up all of your memory. Look, you know, practical numbers are things like 100 or less, the dimensionality. There are variations. If we get time, we can look into where you use restarting, right? So you iterate up to a certain point. You can't afford any more vectors. You're not happy with your estimate. You go back to the start and build up again, but you try to keep some semblance of the information you've generated so far. Mm-hmm. But yeah, that's, you know, that is a way to think about this problem, is that if you can afford the memory to keep those columns, then the accuracy can be improved by taking M larger still.
Yeah, and I guess it also depends on how really sparse your matrix A is. So
I mean, all these iterative methods can be quite sensitive to the properties of the matrix. It's, you know, it's not like a classic direct method where the runtime and the performance is completely predictable. It's very dependent on the actual matrix you give it. Normally the matrix vector products are not, well, I can't say normally. There can be, in fact, there can certainly be situations where the matrix vector product is the most costly step in this whole process. So you may not even want to keep multiplying A by more vectors. You know, depends. Sometimes the matrix doesn't even sit in memory. It's a process, and, you know, calculating A times V is a big effort in itself. So yeah, so that is another factor to consider for sure.
Okay. All right, thank you. So any more questions? Again, I don't see any hands and I don't see any question in the chat.
I guess if people have questions offline, I can, if I hear about it before the next lecture, I can address it then.
Okay.
That's another option.
Yeah, I think that's possible. So maybe I just, because this is our first lecture for this year, so the link, just a kind of announcement for the rest of the week. So the link will still stay the same for the rest of the week, okay? And the recording will be available on YouTube, our YouTube channel. I don't know how long it will take to process, but I think in most cases, if you miss a lecture, you probably would have you probably would have time to watch the recording before the next one. So. Maybe I also, since there is nobody asking questions, so my question, another one. So Arnoldi, this is the process, but before you apply just usual classical Gram-Schmidt orthogonalization process, right? So it's not a kind of modification for this method, right?
So yeah, the thing that Arnoldi brings is that it's on the fly orthogonalization.
Right. Okay.
So what definitely wouldn't work, this is a great question, so I'm glad you asked. What definitely wouldn't work is to build this up by B, A squared B, and then apply a Gram-Schmidt process.
Right.
Okay? Because the damage is done then.
Okay.
You're not going to pull out information that wasn't there already. So you'll get a very nice orthonormal basis, but the ill conditioning will leak into the other matrix. Okay, so all these dot products and norms and things, right? So you don't win there. The conditioning doesn't go away; it just migrates, right?
Right.
So it still sits in your problem.
Yeah. Okay.
The real important step is that the process is done vector at a time. Okay, so again, really good point. We're multiplying VJ here, right? So this is not B. Okay, the space that you're spanning is the same, but the numeric says you multiply the previous vector that you had just orthonormalized by A, right? So we're not getting this Powell method type convergence to a single direction. We definitely don't want.
Okay. Actually, now we have questions in the chat, right?
Yeah. Okay. So I'm very happy to put the MATLAB notebook somewhere if it helps, and the slides, and just anything. I can provide all of this stuff. Very happy to do that. Just let me know where and how.
Yeah, maybe we can upload on our MoCaO website. So Tim, if you are happy, so you can email the script to me and I will upload it on our website.
Yep, that sounds fine. Yep.
All right. Yeah.
Yeah, you can play around with it. Those in the audience can experiment and get an intuition that way too.
So I just don't know if we can upload MATLAB files because I never tried. I mean, it's definitely no problem with documents and images. So, but if somehow it doesn't work, a kind of straightforward method, then we will find some way to get around it.
Okay. Sounds good.
Yeah. Okay. So, yeah, thank you very much. So, I guess today we can finish within 1 hour. So
well, I'll do my best to keep it to the hour. If I have too much to say, I'll try to compress it down.
Okay. Yeah, I think that's great, and everybody can. I mean, already some people need to go. So tomorrow we will continue, right? So this is.
Yep, we'll pick up the same thread tomorrow and start to analyze what we can expect with which eigenvalues you get and so on. Yep.
All right. Okay. Well, thank you very much. Thank you.
Thank you, and thanks everyone who was there.
Yeah, thank you, and see you all tomorrow.
Okay.
Bye.
Bye.